system of particles, I would like to show you a complex example. So the complex example means that this example has some phases, and we will solve them independently, and we will go from one phase to another one sequentially. So first, what happens? So we have two particles with mass m1 and with mass m2. What is given? And at the beginning of the process, this particle 1 is a part of the mathematical pendulum. There is a diameter of pendulum r, and it is waiting at this position until anger this particle m1 is a part of the pendulum with diameter r and is waiting at the beginning of the process elevated under angle phi at position A, and simultaneously particle m2 is waiting for impact with or collision with pendulum. So the initial velocity of both particles is 0. After that, we release the pendulum, and the pendulum is going down and step into collision with m1, m2. So there some collision happen, and we assume it is real collision, so we will use Newton's theorem. So system of particles loses some amount of energy here during the collision, so the resilience position of pendulum will not be exactly phi again, but it will be less. So pendulum is going to lower position than it was before collision. Before, pendulum lost some energy during collision. In opposite, particle m2 got some energy from the collision and is going right and with some velocity, and because the surface is rough, so it will slowly until it stops finally, and it stops at the position LD, and the task is to calculate this position LD where particle m2 will arrive and angle phi c. This is the highest position of pendulum after collision. So that's all, and now we can separate this complex phenomenon to some more simple phases. So the phase 1 is that pendulum is going down, and it's getting, by the way, some kinetic energy. So we use a balance of energy, so we can say that because we don't lose energy during this motion, we can use law of conservation of mechanical energy. So this is abbreviation of mechanical energy, and it is like this. So energy, the sum of energies of mass 1 at point A is equal sum of energies of the same particle at place B. So this particle has some potential energy, and this amount of potential energy is changing it to kinetic energy. Let's say that zero level of potential energy is here. So I think we called potential energy V. Potential energy V. So we need to calculate this height, this size, and it is so it is mg by h. Let's say h0. It's a potential energy of particle 1, where h0 is here. This is h0, and all this energy is changing during the motion to kinetic energy. So it is a 1/2 of m1 v1. So this is a velocity of particle 1 at place B. About first particle we worry nothing, because it stays at place, at rest, doesn't move. So we need to express h0. So you can look at the image and you can find that it is r plus r by cosine 2p minus VA. So it is equal a half of m1 v1b square. This is m12. So we can cancel m1 and we can put out the brackets r. So it will end like this. So this is 1 minus cosine phi a, because cosine 2 pi minus phi a is this, and it is equal a half of v1b square, and from this we can calculate the final velocity of phase 1 for mass 1, that it is 2gr by 1 minus cosine phi a square root of. So this is the end of phase 1, where the particle number 1 is here, is going into the collision, and particle number 2 is waiting for collision. So now we can approach the phase 2. What is real collision? Real collision. For this we will use law or Newton's theorem. Newton's theorem. It's shown in the theory, so I will not write it again, but I only emphasize that Newton's theorem is epsilon is minus v1 minus v2 star star 1 2. Yeah. And if we use it and in combination with law of conservation of momentum, so we can find the result that v1b after collision is minus v1b, it means before collision, by epsilon m2 minus m1 plus m2, And similarly, V2 at place B after collision is 1 plus epsilon by m1 v1 b over 1 m1 plus m2. So how we got this? So first we used Newton's theorem, and second we use law of conservation of momentum. So we can look at theory about real collision, and you can see here that we derive these results, and if we use as an input the original velocity is equal to 0, so v1 and v2 are zeros, so it means velocity is before collision, so we get so if we look at the theory conclusion, so we can see that there are general results under circumstances that v1 and v2 are not zero. For in our case, the original velocity before collision of particle 1 is known, calculated from energy balance, and original velocity of particle 2 is 0. So if we substitute 0 for v2, so we can cancel this and this, and finally we get these shortened results. So let's continue. Phase 2 is finished, and we know the output velocities from the collision. So we know velocity of particle 1 after collision and velocity of particle 2 after collision. So let's go to phase 3. Phase 3 is about the independent motion of both particles. Let's say that we will deal with pendulum first. So now we will calculate the final highest angle over silence motion of pendulum. So how high particle M2 will go up. So we can use a very similar procedure as it was used in phase 1. So there is a pendulum with mass m1 r and with velocity v1 at b after collision. So it's an initial situation of this phase, and it goes up to some angle, okay, and we need to calculate this angle. So what is this high height? So it is h1. So we use as the same approach as previously, so energy balance, where we say that all, or more specifically we use law of conservation of mechanical energy. So we say that kinetic energy of first particle with velocity after collision will change all to the potential energy of particle 1. So from this we can cancel m1, and from this we can calculate the angle. So h1 here is r by 1 minus cosinus phi c, and from this we need to calculate phi c. So we can say, because v1b, we can say that v1b is from here, v1b by epsilon m2 minus m1 over m1 plus m2 and square root 1/2. So it is equal 2 by gr 1 minus cosine phi c. So so this is from previous calculation, and we substitute it for this, and is equal this. v1b is known from previous calculation, so I can put it into the bracket. So v1b was square root 2gr 1 minus cosine phi a, and we can substitute it for this. So I can write 2gr 1 minus cosine phi a by epsilon m2 minus m1 square root m1 plus m2 square root is equal to gr 1 minus cosine phi c. So we can cancel all this, and we can calculate phi c from here. So phi c is equal like this. Phase 4 is about independent motion of particle 2. So when it goes from collision, so there is original position of particle m2, and it goes from collision with velocity v2 star, and because the surface is rough, so it will end at some distance LD, and we would like to calculate this distance. So because there is a non-potential field, because on one side there is gravity field, what is by nature the potential force field, but there is also friction force, and the friction loses energy, cause losing energy, and it's non-potential phenomenon. So all over, in combination of G, gravity field, and friction force, we get non-potential force field. So we need to use law of conservation, or change, law of change of kinetic energy. Why? Because we have non-potential force field. non-potential force field. So we can write that kinetic energy at place D minus kinetic energy at place B, this is B place, this is D place, is equal integral from R1 to R2 FdR. So KD, kinetic energy at place D, is 0 because particle stops at this place, and kinetic energy before, so at the beginning of phase 4, is 1/2 of m2 v2 star square, and it is equal to what? So we go from here to here, so the distance is LD and it is rectilinear motion, so we can calculate this integral in scalar form. So it is integral from 0 to LD of f dx, where x is the axis. So we must calculate this resulting force acting to the particle. So we must draw free body diagram somewhere at general position. So let's say if it is going from the beginning to the end, so anywhere between beginning and end of the motion. So which forces are acting to the particle? So first there is gravity force, and second there is a normal force from the supporting. So free body diagram is a scheme where we draw all forces acting to the particle. So this is particle 2. First there is a gravity force acting downwards. Against upwards there is a normal force as a reaction between a particle and the rigid base. Left there acts friction force against motion, and that's all. So if we write an resulting force, so the part of resulting force in x direction, it is minus ff, because plus x direction is it's here, so resulting force in x direction is minus ff, and second resulting force in y direction is 0 because g and n are in balance. The particle make no motion in y direction, so there is balance of force equilibrium, but there is not force equilibrium in this direction. Okay, so these are, so we can write index R resulting force here. Okay, so these are components of this resulting force, and because the particle makes motion only in x direction, so we don't need to pay attention to y direction because it doesn't move in this direction. So we can substitute into this equation, so we can continue. It is 1/2 of m2 v2 square with star is equal integral from 0 to LD minus f dx, and from this simple equation we can calculate that normal force is equal gravity force, and gravity force is equal m2 by g. Okay, and friction force usually by Coulomb theorem is given friction coefficient by n, so it is Fm2g. Okay, so this is friction force Fm2g, and we can substitute it here. So we can write it again, is equal integral from 0 to L minus Fmg dx, and all these parameters are constant. So we can put them out of the integration, and we can integrate only dx in limits from 0 to LE. So it is minus Fmg LD. And now we compare these sides of equation. So it is minus a half m2 v2 square star is equal minus fm2g LD. We can cancel m2 and we can calculate the final length of the motion. So we can cancel also minuses. So LD is equal v2 star square over 2gf. And I forgot to write B index here. B. So that's all.